Hello everyone. So, till now we considered hydrodynamically and thermally fully developed flow. So, in analysis it was easier because the non-dimensional temperature phi whatever we defined, it was function of r only. So, it does not change in the axial direction. Today we will consider hydrodynamically developed, but thermally developing laminar fluid flow through circular pipe with uniform wall heat flux. So, you can see that it is thermally developing flow. That means, your temperature will change in axial direction and it will vary only inside the thermal boundary layer. However, in the core region it will remain at the inlet temperature. So, let us see. So, this is your circular pipe of radius r naught. We have kept the axis at the center line and at x equal to 0 we have put in such a way that from there uniform heat flux boundary condition is applied. If x less than 0, then both the fluid and wall have uniform temperature Ti. So, after x greater than equal to 0 you have uniform wall heat flux boundary condition and your thermal boundary layer starts growing from x equal to 0. So, this is your thermal boundary layer thickness. So, we have considered hydrodynamically fully developed flow. So, you have velocity u which is function of r only and it is fully developed profile parabolic. However, your temperature profile you can see that it will vary inside the thermal boundary layer only, but in the core region it will remain at temperature Ti. The assumptions for this study are axisymmetric steady incompressible laminar flow with constant properties. You can see that it is geometrically and thermally symmetric and we can have the assumptions of axisymmetric flow. So, there is no variation in of any quantity in circumferential direction. It is hydrodynamically developed flow, that means del u by del x is 0 and radial velocity v is 0. It is thermally developing flow. We used uniform wall heat flux condition. In this particular case also we will neglect the axial heat conduction. That means, axial heat conduction is, we will assume that axial heat conduction is very small compared to the radial heat conduction, and we will also assume negligible viscous heat dissipation and no internal heat generation. So, the problem hydrodynamically developed and thermally developing flow inside a circular pipe is known as Gray's problem. So, we will define the Gray's number as Reynolds number into Prandtl number divided by x by d. So, you can see that this is some inverse of non-dimensional form of the axial distance. Okay, x is the axial distance, and if you put the variables in Reynolds number and Prandtl number, you can write it as d square by alpha x is equal to d square by alpha divided by x by So, you can see that in the numerator and denominator both are having the time scale, where d is your 2 into r naught. So, Gray's number represents the ratio of the time taken by heat to diffuse radially into the fluid by conduction to the time taken to the fluid to reach distance x. For small values of Gray's number, radial temperature profiles are fully developed. So, you can see that if x is very high, then your Gray's number will be small. So, if x is very high, it will be thermally fully developed flow. So, Gray's number will be small. So, for small values of Gray's number, radial temperature profiles are fully developed, but for larger values of thermal boundary layer development has to be taken into account. So, you can see if x is very small, then it will be thermally developing region. So, before going to the analysis, first let us consider this second order ordinary differential equation. So, this is your second order ordinary differential equation d of dx p d phi n by dx plus q plus lambda n square w into phi n. So, this is known as Sturm-Liouville equation or Sturm-Liouville boundary value problem. Here lambda n square is known as eigen values and phi n is the solution of this ordinary differential equation and it is the eigen functions associated with each lambda n. Okay. So, if p, q and w are real and boundary condition at x equal to a and x equal to b are homogeneous, then you will get harmonic solution in homogeneous direction. The function wx plays a special role and is known as the weighting function. In today's analysis, we will use separation of variables method. So, when can we use separation of variables method? If your governing equation is linear and homogeneous and in one direction if you have two homogeneous boundary conditions and this, then you can use the separation of variables method, and when you will separate the variables then it will be equal to some constant and the sign of constant you need to choose such a way that in homogeneous direction you will get harmonic solution. So, we have to choose the lambda n square or the constant such a way that in homogeneous direction, that means in that direction where you have two homogeneous boundary condition, it should give harmonic solution. So, you can see, so if you can resemble your governing equation with the Sturm-Liouville equation and p, q, w are real and boundary condition at x equal to a and x equal to b are homogeneous, then you will get a harmonic solution in the homogeneous direction. One important property of this Sturm-Liouville equation is orthogonality. So, you can see two functions phi n and phi m are orthogonal to each other in the range a b with respect to weighting function w x if integral a to b phi n phi m into w dx equal to 0 for n not equal to m. So, now for n not equal to m, this integral will be 0. So, it will be used to find the constant when we will use the separation of variables method. Now, first let us consider hydrodynamically and thermally fully developed flow through the circular pipe with uniform wall heat flux boundary condition. Already we have studied it, you know the solutions, just we will represent this solution again here. So, you can see that fully developed velocity profile is this one, where um is the mean velocity or average velocity. The temperature T xr, which is your fully developed temperature profile, is equal to in Tw minus 3 by 4 q double prime w r naught by k into 1 minus 4 r square by 3 r naught square plus r to the power 4 divided by 3 r naught to the power 4. So, this already we have derived the fully developed temperature profile in terms of Tw. Again we have derived the mean temperature in terms of wall temperature. So, you can see Tm is equal to Tw minus 11 by 24 q double prime w r naught by k. So, if you substitute Tw in this equation, then you will get this equation. So, the temperature profile we have written in terms of mean temperature. Again from energy balance we have derived this equation. You see Tm is equal to Tmi plus q double prime w p into x divided by m dot Cp. So, you know that p is the perimeter, where in this particular case it is twice pi r naught, and m dot is the mass flow rate, rho um pi r naught square. So, rho u a, area is pi r naught square. So, this already we have derived from the energy balance, and where Tmi is the at inlet you have the mean temperature. So, this p and m dot, this value if you put, then you can write in this form. Now, this Tm value you put in this equation. Okay. So, if you put, you will get this equation. Okay. So, this Tmi if you take in the left hand side and divide by q double prime w r naught by k, then you can write in terms of a non-dimensional quantity. So, you can see that in this particular case it will become 4 x by r naught, and this after rearrangement you will get Reynolds number into Prandtl number, and this is also non-dimensional quantity. So, you can see that we have written this T. What is this T? T is your fully developed temperature profile. So, in a fully developed condition, fully developed means hydrodynamically and thermally fully developed. So, TFD minus TMI. So, at inlet temperature for this particular case we have Ti, right, we have Ti. So, you will get minus Ti divided by q double prime w r naught by k, and this in the denominator you will get Reynolds number based on diameter into Prandtl number. So, this is the temperature profile, okay, in a fully developed flow, and where TFD we have represented as a fully developed temperature and Ti is the inlet temperature. So, this already we have carried out this analysis earlier, just we have revisited it. Now, let us consider thermally developing flow. So, in thermally developing flow we will consider a temperature Td such a way that your temperature profile at any location, whether it is in thermally developing region or fully developed region, T will be TFD, which is your fully developed temperature profile, plus Td. So, you can see here this is our problem. Now, in developing region, thermally developing region, you can see your thermal boundary layer thickness is growing, okay. So, it is your developing region, thermally developing region. So, the temperature profile, let us say T x T, which is function of x and r. This temperature profile we need to find for thermally developing region, but this T is valid for both in thermally developing region as well as thermally developed region, okay. And we are defining this temperature as TFD, which is your fully developed temperature profile plus some temperature Td, okay. So, which is we will consider only in the developing region, and in fully developed region this Td will become 0. So, in fully developed region, thermally fully developed region, so in thermally developed region, this Td will be 0, okay. So, we are defining Td in that way. So, you see we need to find T which is valid in thermally developing region and thermally developed region. This TFD we have already derived, which is your temperature profile in thermally developed region. Now, you can see that this red color profile is your TFD and this is your green color profile, this is your TXR. So, obviously you can see your in axial direction in the core region, in a thermally developing region you can see that it will be always Ti, because that is the temperature, inlet temperature, okay. Only temperature is varying inside the thermal boundary layer. So, in the core region temperature will remain at Ti. At another location if you consider, here also it will be Ti, but once it becomes fully developed region then your core temperature will vary. So, obviously the temperature profile in the thermally developing region will be lesser than the fully developed region. This is also true for the wall temperature, because at the wall temperature you can see this is a constant wall temperature, this is the constant wall heat flux boundary condition. So, Tw will be function of x, and along axial direction your Tw will increase. So, obviously when it will come to fully developed region, obviously your Tw will be higher than the Tw at developing region. So, we have represented this green color temperature profile in the developing region, red color temperature profile in a fully developed region. So, the difference we are representing with Td. So, you can see this is actually negative, okay. This is actually negative, but we are considering T, which is your temperature profile at any region, whether it is thermally developing region or thermally fully developed region, is equal to TFD plus TD. So, you can see that your TD will be maximum at x equal to 0, okay. TD will be maximum at x equal to 0, then it will start decreasing, decreasing, decreasing. Once it becomes thermally fully developed region, then your TD will become 0. So, from the high negative value to 0, it will vary in the developing region. So, you can see that when it is fully developed region, TD will become 0 and TXR will be just TFD, and in developing region TD will have some negative value. So, this negative value will be deducted from TFD and you will get the green color, this temperature profile. So, I hope you have understood that how we have defined a temperature in the developing region TD, which is actually negative quantity, and this is having a high value at x equal to 0 at the entrance region, and it will decrease along axial direction in the thermally developing zone. After that, once it becomes thermally developed region, this TD will become 0 and your temperature profile T will become TFD. So, this TXY we need to find, which is valid in both thermally developing region as well as thermally developed region. So, now let us write the energy equation invoking all the assumptions. Okay. So, you can write, this is the energy equation, U del T by del x equal to alpha by R del of del R del T by del R, where alpha is your thermal diffusivity. So, in fully developed region our temperature profile is TFD. So, obviously this TFD will satisfy this governing equation. So, you can write U del TFD by del x is equal to alpha by R del of del R del TFD by del R. So, now if you subtract this equation from this equation, so what you will get? You will get U del TD by del x is equal to alpha by R del of del R del TD by del R. So, where TD is your T minus TFD. Okay. From this definition you can see your TD will be T minus TFD. So, you can see that the whatever temperature TD we have introduced in the thermally developing region, it also satisfies the energy equation. So, now we need to solve this equation first and we will find the TD. We know already TFD. So, the temperature profile TXY we can write TFD plus TD. Now, aim is to find the temperature profile TD. Okay. So, first let us write the boundary conditions for TD. So, boundary conditions are at x equal to 0, okay. So, you have T is equal to Ti and we know T D is equal to T minus TFD, right. We have defined this way. So, if at x equal to 0 T is equal to Ti, we will get TD is equal to Ti minus TFD at x equal to 0. Okay. Now, in radial direction the boundary conditions are at r is equal to 0. Okay. At r is equal to 0 you can see that your due to the axisymmetric condition, as it is thermally and geometrically symmetric, you will get maximum or minimum temperature at the central line where r is equal to 0. So, that means the temperature gradient with respect to radius will be 0. So, you will get del T by del R is equal to 0, and in fully developed case also you can write del TFD by del R is equal to 0, because already we have imposed this boundary condition. So, you can see from here you can write del TD by del R is equal to del T by del R minus del FD by del R. So, if del T by del R and del TD by del R are 0, then obviously del TD by del R will be 0. So, you can write del TD by del R will be 0 at R is equal to 0, and at the wall at R is equal to R naught, okay, we have the heat flux boundary condition. Okay. So, you can see q double prime w we have taken in the negative radial direction. So, what will be your q double prime w? So, it will be k del t by del r. We are not writing minus sign because q double prime w sign is in the negative to radial direction. That is why it is positive k del t by del r at r is equal to r naught is equal to q double prime w. Okay. So, this is your for del t by del r. So, now what is T? T is your T d plus T f d, right, and for a fully developed boundary conditions also we have applied this Worley heat flux boundary condition. So, you will get K del T d by del r at r is equal to r naught also will be q double prime w. Okay. So, now if you subtract, okay, these two, so what you will get? If you subtract, then you will get k del of del r t minus, sorry, this is your T f d. So, in the fully developed case where thermally and hydrodynamically fully developed region, your temperature boundary condition at r is equal to r naught will be k del T f d by del r at r is equal to r naught is equal to q double prime w, because already we have solved for this boundary condition, right. So, now if you subtract this equation from this equation, what you will get? K del T minus T f d divided by del r at r is equal to r naught is equal to 0, right. And what is T minus T f d? It is nothing but T d. So, that means you will get del T d by del r at r is equal to r naught will be 0. So, you see in the radial direction at r is equal to 0 and r is equal to r naught, your temperature gradient of T d, okay, is 0. Okay. So, that means both the boundary conditions are homogeneous, that means it is the homogeneous direction. So, when we will use separation of variables method, we have to choose the sign of the constant such a way that you will get the harmonic solution in r direction. So, now our governing equation is u del T d by del x is equal to alpha by r del of del r into del T d by del r, because we need to find this value of T d, right, because T f d is known. If T d you can find, then the temperature profile in general you can write T f d plus T d. In this case we are using hydrodynamically developed flow, that means u you know. So, u you can write twice u m into 1 minus r square by r naught square. Okay. So, you can write fully developed velocity profile, okay, you know u is equal to twice u m into 1 minus r square by r naught square. So, you put it here. So, you will get twice u m 1 minus r square by r naught square is equal to alpha by r del of del r del T d by del r, here del T d by del x. Okay. So, now let us define some non-dimensional parameters. So, we will use the radial direction eta is equal to r by r naught. So, this is your non-dimensional radial direction, and the non-dimensional axial direction eta will define as x by r naught divided by Reynolds number into Prandtl number. So, let us introduce non-dimensional parameters as follows. So, eta as r by r naught. So, you can see this is your non-dimensional radial coordinate. Okay. Then zeta we will write as x by r naught divided by Reynolds number based on diameter into Prandtl number. So, this is your non-dimensional axial coordinate, and the non-dimensional temperature theta d will define as T d divided by q double prime w r naught by k. Okay. Where T d is nothing but T minus T f d, right, divided by q double prime w r naught by k. Okay. So, now if you put all these values, so you can see you can write T d is equal to q double prime w r naught by k into theta d. So, you can write del T d by del x as q double prime w r naught by k, okay, del theta d by del x. So, you see theta d is function of both zeta and eta. Okay. Then you can write this x coordinate, okay, in terms of zeta. So, you can write q double prime w r naught by k. So, this x you substitute with eta. So, it will be Reynolds number into Prandtl number into r naught del theta d by del zeta. Okay. So, Reynolds number Prandtl number into r naught, this if you write you will get q double prime w r naught by k. Okay. So, Reynolds number into Prandtl number into r naught, what it will be? So, rho u m twice r naught by mu, this will be mu C p by k into r naught. So, you can see this mu will get cancelled. Okay. So, you can write twice u m r naught square. So, k by rho C p, okay, k by rho C p is your thermal diffusivity. So, you can write alpha by twice u m r naught square into del theta d by del zeta. Okay. Similarly, you can write del T d by del r is equal to q double prime w r naught by k del theta d by del r. So, now this r will put as r naught into eta. So, you can write q double prime w r naught by k, okay. Then you will get 1 by r naught del theta d by del r. Okay. So, del eta. So, this r naught if you cancel it, then you will get q double prime w by k del theta d by del eta. Similarly, if you write del of del r into r del T d by del r, you can write as q double prime w by k del of del eta into eta del theta d by del eta. Okay. So, all the derivatives we have found. Now, all these you put it in the governing equation, okay, in this equation, and write it as twice u m into 1 minus eta square, because r by r naught is eta. Then you have q double prime w r naught by k, then you have alpha by twice u m r naught square del theta d by del zeta is equal to alpha by r naught into eta q double prime w by k del of del eta into eta del theta d by del eta. Okay, after substituting all the terms. So, now you can see here this alpha you can cancel, um 2 2, okay. This r naught here you will get 1 and another this r naught, so you can cancel q double prime w, q double prime w, k and k. Okay. So, you can write the final equation as 1 minus eta square del theta d by del zeta is equal to, okay, you can write 1 by eta del of del eta into del theta d by del eta. So, now we will use separation of variables method. So, what is separation of variables method? We will write the solution of theta d as a product of two individual solution x and r, where each solution is function of one coordinate only. So, like we are defining theta d as product of x and r, where x is function of zeta only and r is function of eta only. So, before going to that, let us write the boundary conditions. Boundary conditions at zeta is equal to 0, that means x equal to 0. So, theta d you can write T I minus T F D at zeta is equal to 0 divided by q double prime w r naught by k, and at eta is equal to 0 you have del theta d by del eta is equal to 0, and at eta is equal to 1 because r is equal to r naught. So, eta will be 1, del theta d by del eta will be 0. Now, we will apply separation of variables method. So, we will write the solution theta d which is function of zeta and eta as product of two individual solution x which is function of zeta and r which is function of eta only. So, you can see we are writing product of two solution x and r, where x is function of zeta only and r is function of eta only. So, when can you use separation of variables method? If the governing equation is linear and homogeneous, okay, and in one direction you have two homogeneous boundary conditions, then you can use separation of variables method. So, you can see our governing equation, this equation is linear and homogeneous, and in eta direction you have homogeneous boundary conditions. Okay. That means eta is your homogeneous direction. So, eta is your homogeneous direction. Okay. So, we can use separation of variables and we are writing the solution theta d as product of two individual solution x and r, where x is function of zeta only and r is function of eta only. Okay. So, now let us write del theta d by del zeta as r into, because r is function of eta only. So, you can write dx by d zeta. So, now this is your ordinary derivative we are writing because x is function of zeta only. Similarly, you can write del theta d by del eta, okay. So, that you can write as x into dr by d eta. Okay. So, similarly, if you write del of del eta, eta into del theta d by del eta, then it will be just d of d eta into eta d r by d eta and one x will be there. Okay. So, all these derivatives you put it in this equation. Okay. So, what you will get? So, you will get 1 minus eta square r into dx by dz d is equal to x into d of d eta dr by d eta. Okay. Then you can write as 1 by x dx by d zeta, okay, is equal to 1 by, so one governing equation is one eta is there, okay, 1 by eta. So, it will be divided by eta. So, you will get 1 by r into 1 minus eta square into eta, okay, d of d eta into dr by d eta. Okay. So, you see this equation, left hand side x is function of zeta only, that means the whole term, left hand side term is function of zeta only. Right hand side if you see, r is function of eta only, and right hand side all the terms are function of eta only. So, left hand side is function of zeta, right hand side function of eta. So, this will be equal to some constant, okay, because left hand side is your function of zeta, right hand side function of eta is equal to some constant, and that constant sign you have to choose such a way that in eta direction you should get the governing equation such a way that you will get the harmonic solution of that governing equation. And obviously, if you can write in r direction the governing equation as Sturm Liouville equation type, then you will get the harmonic solution in eta direction. So, we will choose the constant as minus lambda n square, where lambda n square is your eigenvalues. So, you can write 1 by x n. So, for different value of lambda you will get different solution. So, now this x and r will write in terms of n. So, you will get dx n by d zeta is equal to minus lambda n square, okay, and this you will get dx n by d zeta as minus, sorry, dx. So, you will get dx n by x n. So, you will get dx n by x n as minus lambda n square d zeta. So, you can see its solution will be exponential. The other term you will get 1 by r into 1 minus eta square into eta d of d eta into dr by d eta is equal to minus lambda n square. Okay. So, you can see this will be your d of d eta into eta dr. So, we will write r n, because for different value of lambda n you will get different solution, right. So, r n. So, we will get d r n by d eta, okay, plus lambda n square 1 minus eta square into eta into r n is equal to 0. Now, you see this second order ordinary differential equation, you compare it with the Sturm Liouville equation. Okay. So, you can see your, if you compare with the Sturm Liouville equation, P is your eta, okay, Q will be 0 and the weighting function, okay, W is 1 minus eta square into eta, and okay, these are real, and in eta direction you have two homogeneous boundary conditions. So, obviously, you will get the harmonic solution in eta direction. So, if you see this second order differential equation, okay, it is very difficult to solve. So, you can use some numerical technique to solve this second order ordinary differential equation. Once you get the solution which is at the eigen function of this equation R n, then you can write the product of these two solutions, one you will get from the x, another solution from r, then this product of these two solutions will be your the temperature profile theta t. Okay. But for different values of eigen values lambda n square, you will get different solution x n and different solution R n. Okay. So, you need to find what is the value of lambda n, okay, eigen values. Numerically, if you solve this equation, okay, with the proper boundary conditions, then you will get the eigen functions of this ordinary differential equation R n. Then you can write the solution theta d, okay, as summation of all the product of solution x and r, because for different values of lambda n, okay, you will get different solution x into r. Okay. And as it is a linear solution, linear governing equation, so you can superimpose all the solutions for different values of lambda n. Okay. And if you superimpose, that means you are adding all the solutions. So, it is possible as you have the governing equation linear, okay, because you have a linear governing equation. So, you can superimpose all the solutions. So, now let us write the final solution theta d as product of x n R n, where x n is the solution where you will get in the exponential form, R n you need to find solving this second order ordinary differential equation. Then you can sum it from n is equal to 1 to infinity, because you will get different values of lambda n and you will get the different solutions. Okay. So, assuming that your solution of this second order differential equation is R n, which are eigen function, and lambda n square is eigen values, then you can write the final solution as, so you can write the final solution theta d, which is function of zeta and eta, as summation of n is equal to 1 to infinity, the constant C n, okay, R n, these are the eigen function of this second order differential equation, and this is the solution, okay, this is the solution from the eta direction. So, the first equation you can see. So, if you solve this equation, okay, so you will get x n is equal to some constant into e to the power minus lambda n square d zeta. Okay. So, this product if you write R n if you find and x n if you find, then you will get the final solution theta d as product of two individual solutions, and as it is linear equation, you can superimpose all the solution n is equal to 1 to infinity for different values of lambda n. Okay. So, R n you need to find. Okay. So, this is the eigen functions of this second order differential equation. Okay. So, now we need to apply the boundary conditions, okay, to find this constant C n, as well as you need to find lambda n square, because that is also unknown. So, you can see the temperature profile for hydrodynamically and thermally fully developed fluid flow we have written like this, okay, we have already derived today. So, in non-dimensional form if you write, so T f d by q double prime w r naught by k, you can write theta f d, okay, and T I by q double prime w r naught by k, you can write theta I. So, theta f d minus theta I as this is your 4 zeta plus this is your eta square minus eta square, sorry, eta 4. So, this is eta to the power 4 by 4 minus 7 by 24. So, now theta d we have defined T d by q double prime w r naught by k, and T d is nothing but T minus T f d, okay, that means theta minus theta f d. Okay. So, now apply the boundary condition at eta is equal to 0, okay, at eta is equal to 0 we know theta d is equal to T I minus T f d as eta is equal to 0 divided by q double prime w r naught by k. So, this we already we know. So, you can see that, okay, so this is your theta d, and you can see here, okay. So, from this, okay, if you put at eta is equal to 0, that means this is your at x equal to 0, right. So, you can write theta d as what is this? This is nothing but theta I minus theta f d, okay, at zeta is equal to 0. Okay. So, you can write it as theta I minus theta f d at zeta is equal to 0. So, you can see from this equation, okay, from this equation if zeta is equal to 0, if you put, so and if you reverse it, so you will get this as minus eta square minus eta to the power 4 by 4 minus 7 by 24, okay, is equal to summation of this one n is equal to 1 to infinity C n into R n, because e to the power minus lambda square into zeta, that means sorry, this is your zeta is equal to 0. Okay. At zeta is equal to 0, x equal to 0. So, theta d is this. So, you can write e to the power minus lambda square zeta. So, that means e to the power 0, it will be 1. So, C n into R n. Okay. So, now we need to find the constant C n. Now, we will invoke the orthogonality constant. So, now we will invoke the orthogonality condition what we discussed in the Sturm-Liouville equation. So, what we will do now, multiply both side by okay, weighting function w into R m into d eta and integrate between 0 and 1. Okay. So, this w is the weighting function. What is this? You can see here 1 minus eta square into eta. Okay. This is your 1 minus eta square into eta. So, if you multiply and integrate it, so you will get so this is your w, then R m d eta is equal to 0 to 1, okay. Then you can write summation of n is equal to 1 to infinity C n, okay. Then you can write R n into R m into 1 minus eta square eta d eta. So, if you remember the orthogonality condition, for n not equal to m, okay, integral 0 to 1 R n R m into w d eta will be 0. Okay. So, you can see from here. So, summation of n is equal to 1 to infinity. So, for n not equal to m, you can write, use the orthogonality condition, zero to 1 R n into R m into eta 1 minus eta square d eta is 0 for n not equal to m. C n is constant. So, C n you take outside. Okay. So, obviously, for n not is equal to m, this will become 0. So, only for n is equal to m, only one term will remain. Okay. So, if you write for n is equal to m, if you keep, then you can write 0 to 1 minus eta square eta to the power 4 by 4 minus 7 by 24, okay, eta into 1 minus eta square R n d eta is equal to C n into 0 to 1 eta 1 minus eta square R n square d eta. Okay. N is equal to m we have put. So, now you can find the constant C n. 0 to 1 eta square eta to the power 4 minus 7 by 24 eta 1 minus eta square R n d eta divided by 0 to 1 eta 1 minus eta square R n square d eta. So, you can see that if R n is known, okay, which is the solution you will get from the second order differential equation, then you will be able to integrate this and you can find the constant C n. Okay. Now, we need to find the value of lambda n. So, first we will start from the governing equation. So, what is your governing equation? We have d of d eta eta d r n by d eta, okay, plus lambda n square eta 1 minus eta square r n is equal to 0. So, this is the equation we have derived, you can see. So, this is the equation. Okay. So, now you integrate between 0 and 1. Okay. Integrate the above equation between 0 and 1. Okay. So, if you integrate, so you will get 0 to 1 d of eta into d r n by d eta is equal to minus 0 to 1 lambda n square eta into 1 minus eta square r n d eta. Okay. So, this equation you just write in the left hand side. So, it will be 0 to 1 lambda n square eta 1 minus eta square r n d eta is equal to, now what you will get, you see, you will get integration if you do. So, you will get eta d r n by d eta at eta is equal to 1 minus eta d r n by d eta at eta is equal to 0. Now, you recall the boundary conditions. Okay. At eta is equal to 0 and eta is equal to 1, you have del theta d by del eta is equal to 0, and theta d is a product of x and r, but r is only function of eta. So, your boundary condition at eta is equal to 0 and 1, you will get dr by d eta 0. So, that means boundary condition at eta is equal to 0 and at eta is equal to 1, you will get drn by d eta as 0. So, you can see that these two terms will become 0. Okay. So, hence you will get 0 to 1 lambda n square eta 1 minus eta square r n d eta is equal to 0. Okay. So, from here we can get the eigen values lambda n square, because for you can see this is the condition. Okay. So, this r n if you find, so for different lambda n you will get different r n. So, r n if you know, then from here it should, to satisfy this, because to right hand side will be 0. So, to satisfy this you can find the value of lambda n square from this equation. Okay. So, now if you put the theta d, okay, solution, that is your t minus t f d divided by q double prime w r naught by k, okay, as summation of n is equal to 1 to infinity c n r n e to the power lambda n square zeta, okay, is equal to n is equal to 1 to infinity c n r n e to the power minus lambda n square x by r naught, okay, divided by r e d into Prandtl number. So, you see, now we are interested to find theta, which is the temperature distribution in general. Okay. So, that now you can write, and T f d minus T I also we know, this we have derived, okay, for the fully developed temperature profile. So, this is 4 x by r naught divided by r e d into Prandtl number plus r square by r naught square minus 1 by 4 r naught, sorry, r to the power 4 divided by r naught to the power 4 minus 7 by 24. Okay. So, combining these two you can see. Okay. So, this if you add it, then T f d will get cancelled, then you will get T minus T I. Okay. So, that means you can write combining the above two equations, okay, you will get T, which is function of x and r, which we are interested to find, is equal to T I plus q double prime w r naught by k into 4 x by r naught RED Prandtl number plus r square by r naught square, okay, minus 1 by 4 r 4 by r naught 4 minus 7 by 24. Okay. So, this is your solution from TFD, and now you have to add this TD part. So, you will get n is equal to 1 to infinity Cn Rn e to the power minus lambda n square x by r naught divided by RED into Prandtl number. So, you can see this is the final temperature distribution TXR which we are interested to find, and this TXR is valid in both thermally developing region as well as fully developed region, and you can write in terms of Ti. Okay. So, you can see this is the equation and this is the complete solution. Okay. So, now if you see this eigen functions, okay, you will get different eigen function, but at eta is equal to 1, okay, Rn 1, okay, this is found by these first 7 values of eigen values and functions. These are eigen functions were obtained by Siegel, Sparrow and Hallman. So, you can see from this table. So, for different values of n 1 to 7, these are the lambda n square value, and Rn 1, that means at eta is equal to 1. Okay. So, that means at the boundary, okay, Rn 1. So, you can see this is the first value is negative, and if Rn is negative, then theta d will be negative. Theta d is negative, then you can see that it is a negative quantity Td whatever we defined. So, actually in the developing region you are calculating the temperature distribution which you actually subtracting this Td from the TFD part, okay, and this is negative coming, okay, and the constant Cn you can see these are the Cn. Now, we need to find the Nusselt number. So, you can see that whatever theta d we have defined non-dimensional temperature as Td by this quantity and T minus TFD by Q double prime W R naught by K, and similarly fully developed region theta FD you can define as TFD by this, TW is TW by this, and mean temperature theta m is Tm by this, and theta I as Ti by Q double prime W R naught by K. So, we already derived this theta d, right. So, this is just summation of n is equal to 1 to infinity Cn Rn e to the power minus lambda n square zeta. Now, at eta is equal to 1, okay, at the boundary, what is that? Theta d will be W, theta W, okay, sorry, theta will be theta W. So, theta W minus theta FD is equal to n is equal to 1 to infinity Cn Rn at eta is equal to 1. So, in bracket 1 we are writing eta is equal to 1 e to the power minus lambda n square zeta. So, and also we have found the temperature profile for fully developed flow, okay. So, this is the temperature profile. So, you can write TFD, okay, minus theta, so theta FD minus theta I in terms of non-dimensional coordinate, okay, eta and zeta. So, at eta is equal to 1 if you put, so it will get theta FD at eta is equal to 1 minus theta I, and eta is equal to 1 if you put, then 1 minus 1 by 4 minus 7 by 24. Okay. So, this you will get 11 by 24. So, this we have written 4 zeta plus 11 by 24. So, we can write now at eta is equal to 1 this theta w. So, you can see this, if you add these two equations, this equation and this equation. So, it will be theta w minus theta I as 4 zeta plus 11 by 24 plus this. Okay. Once you get it, so now you see the from the energy balance Tm we have found like this. Okay. So, Tm minus Ti divided by Q double prime W R naught by K is 4 zeta. Okay. So, from there you can find. So, in non-dimensional from theta m minus theta I you can write 4 zeta, and we derived that eta is equal to 1 already in last slide, the theta w minus theta I is this one. So, now we can write. Okay. So, you can see if you subtract this equation, okay, from this equation, subtract this equation from this equation, then you will get theta w minus theta m. So, 4 zeta will cancel. So, you will get 11 by 24 plus this term. So, now by definition what is the Nusselt number? The Nusselt number based on diameter is h twice r naught by k. So, h is q double prime w divided by T w minus T m. So, you can see we are defining the Nusselt number based on the temperature difference at the wall and the mean temperature into 2 r naught by k. Now, you can write 2 divided by q T w minus T m by q double prime w r naught by k, and this is nothing but theta w minus theta m, and this already we have found. Okay. So, Nusselt number for this particular case you can see it is 2 divided by 11 by 24 plus summation of n is equal to 1 to infinity C n r n at eta is equal to 1 e to the power minus lambda n square zeta. So, you can see this is the Nusselt number in general. So, this expression is valid for both thermally developing region and fully developed region. So, let us check whether it is true for the fully developed region or not. So, when you will get the fully developed region? When x tends to infinity, that means zeta tends to infinity. So, at zeta tends to infinity, so Nusselt number D will become fully developed Nusselt number, and you can see that as zeta tends to infinity, this term will become 0. Okay. So, this term will become 0. So, you will get 2 divided by 11 by 24, which is nothing but 48 by 11 is equal to 4.36, and this you have already derived, right, for hydrodynamical and thermally fully developed region. Okay. So, this is true, and the temperature profile for this Nusselt number you can see local and average Nusselt number for thermal intense region. So, this is your q double prime w is constant. Okay. So, for this case you can see with x by d, which is your 1 by Gray's number. Okay. If you plot, so Nusselt number it will decrease in the developing region, and once it becomes fully developed region it will become constant. So, you can see that for high Gray's number you can get the developing region. So, let us conclude. So, today we considered hydrodynamically developed and thermally developing flow through circular pipe with uniform wall heat flux boundary condition, and we started with the fully developed boundary condition, and we derived already the temperature profile in that region, and we defined one temperature T d such a way that the temperature profile T you can find in any region as T d plus T f d, and T d is a quantity, a negative quantity which you subtract from the fully developed temperature profile. Then we use the equation for T d, okay, and with the boundary condition we got the governing equation, and we applied the separation of variables method because the governing equation is linear and homogeneous. So, we use the separation of variables method, and using separation of variables method we use the orthogonality constant to find the value of C n. Okay. So, finally, we derived the temperature profile as this, which is valid for both in thermal region, thermal developing region and fully developed region, and the Nusselt number is this, which is also valid for thermally developing region and fully developed region. And you have seen that at zeta tends to infinity, that means in a fully developed region it gives the Nusselt number as 48 by 11, which you already derived, okay, and it is true for the fully developed region. Thank you.